Hello, I'm Sarah Truitt, and welcome to the National Renewable Energy Laboratory, located in beautiful Golden, Colorado. We are standing here in the Energy Systems Integration Facility, where we develop and validate advanced energy technologies and the controls to integrate them into our energy infrastructure. Today, we'll tour a Power Hardware in the Loop testbed, where very soon companies can come to compete to be the microgrid controller that we install here at NREL. Now we'll visit the Power Systems Integration Laboratory, where we will meet with Senior Electrical Engineer Brian Miller.
Hello, I'm Brian Miller with the National Renewable Energy Lab, NREL, where I serve as the Strategic Team Lead for Microgrids. Prior to joining NREL, I served in the U.S. Air Force as an electrical engineering officer, where I designed standalone power systems for remote military bases, as well as microgrids for critical U.S. military installations. Here at the Energy Systems Integration Facility, we test hardware at megawatt scale in electrical, thermal, and control systems, along with our petascale supercomputer to allow us to solve the nation's energy challenges, including the integration of renewables, electric vehicles, energy storage, and microgrids. Microgrids, which can actually be quite large, are power systems capable of operating independently from the main power grid. This provides many mutual benefits when the grid is connected, and of course provides power when the grid is down. However, there are many technical, economic, and regulatory hurdles that are currently slowing the adoption of microgrids. Here in the lab, we have Microgrid Testbeds at the 10 kilowatt, 100 kilowatt, 1,000 kilowatt, and 10,000 kilowatt levels. What makes this great is we can test technical concerns regarding power quality in a lab-based setting without disruption to actual homes and businesses. We can also run economic analysis on many different options to make the best investment decisions. We can also prove in advance to utility companies that our protection schemes can comply to the utility interconnection requirements. Here in the lab, we can test microgrids, develop new technologies, as well as remove a lot of the risk prior to deploying advanced microgrids. Now let's take a tour of an actual microgrid testbed. First, I'd like to show you our outdoor test area. Indoors, we have several small portable load banks, but outdoors we have our 100 kilowatt and 4 250 kilowatt load banks that can replay resistive, inductive, and capacitive loads. This means I can measure real-world facilities and replay those loads here in the lab for microgrid testing. We also have a collection of generators. We have an 80 kilowatt, a 120 kilowatt, and a 300 kilowatt diesel-fired generator with advanced controls, as well as two 30 kilowatt natural gas-fired micro turbines that can also co-generate heat. All of these generation sources have advanced controllers that manage local operation or can be overridden by the master microgrid controller. Here at NREL, we have a variety of solar inverters ranging in size from 5 kilowatts to 500 kilowatts. This unit is 100 kilowatts and is used to convert the DC power from solar panels into AC power for our microgrid. This unit also has advanced grid support functions to help us control the voltage and frequency on our microgrid, as well as accept external curtailment commands when we need to reduce power. We provide DC power to this unit with our 1.5 megawatt DC supply, which can replicate a solar array, and we can replay weather conditions or geographical locations anywhere in the world at any time. Or, by simply replaying a wind profile instead of a sun profile, I can make this inverter replicate a Type 4 wind turbine. The most challenging circumstance for our microgrid is when we have rapid clouding events or wind gusts in the wind example that cause rapid fluctuations in power level, which are very difficult for our microgrid controller to manage. This is our bidirectional inverter, which, like a solar inverter, converts DC energy into AC power. However, this unit also works in reverse and can store AC energy when there's excess as DC power in batteries. In the lab, our DC battery is replicated by a DC supply, which can vary its voltage based on any battery chemistry and state of charge. This unit is bidirectional and can also change back and forth from importing to exporting power many times during the day, which means it's great for smoothing out those changes in power caused by solar or wind elsewhere in our microgrid. The best thing about this inverter is its grid forming. which, unlike a solar inverter, doesn't require the grid in order to operate. This can form its own grid and act like a generator. This means I can turn off all of the fuel-burning generators in my microgrid. This is our Microgrid Controller operations area, where we have our researchers performing the experiments and also observing on their monitors the performance of the Microgrid Controller. These controllers are mounted in server racks on either side of the desks, and they're essential for networking all of the assets together so that they can be optimized. Otherwise, each asset only knows its local variables, and they can't work together in optimal ways. Unfortunately, the networking introduces cyber vulnerabilities that we're also working to mitigate here through our research. In addition, we have real-time simulation platforms that allow us to emulate a whole city or campus and have this equipment react with it and the microgrid controller to reach into these virtual assets and also control them. As the final stop on our tour, this is our Microgrid Switch, which forms the boundary between our microgrid and the main utility grid. This has logic inside that can detect problems in the main utility grid and disconnect very rapidly. It also sends a signal to our master microgrid controller that it has to take over local microgrid operation. Then later, when the main power grid is restored, this sends voltage and frequency information to the microgrid controller so it can synchronize, allowing us to have a seamless transition back to grid-tied operation. Thank you very much for joining our tour today. We look forward to working with different organizations and partners on microgrid research.
Thank you for spending your time with us. The Energy Systems Integration Facility is a designated national user facility, meaning that state-of-the-art laboratories are available to the broader research community. So please, bring us your challenges. We're here to help.